Hello, Math 172 students. This is actually take two. Earlier this morning, I was having some tech issues and I ended up losing part of the video that I recorded live. So I'm redoing it again this afternoon for you guys who weren't able to live stream. I'll try to also condense it a little bit, show you guys all that you need to know, and hopefully give you some pointers on the Desmos activity. So what we're going to look at today is parametric equations, and to try to understand why we're even looking at something new, what is it going to add for us, we're going to take a look at a quick Desmos slide. So you guys should be able to see the screen, and I'm just going to show you the intro page for the Desmos activity that you're going to be working on. So on this particular page, I want you to look at these four pictures for a minute. I'm going to pause. And the question is, which of the four doesn't belong? Hopefully you picked the one in the upper right, quadrant 1, because quadrant 1 is the only one where our graph is there to start and we're not animating or moving somehow. So in all the graphs we've looked at, we understand that graphs can be kind of created and might have meaning that corresponds to time. But what we're going to do is try to make an explicit connection today between graphs that have a particular orientation, meaning they move, or we're showing the direction in which they're created that's different from the reverse in a meaningful way. So we're going to start off with a non-trig example and then move pretty quickly back to incorporating some trig. So what I'm going to do is show you a little bit on Desmos, what Desmos can do in terms of creating graphs for us. And then we're going to switch over to the tablet. So I'm just going to open up a blank Desmos page. And when we take a look at parametric graphing, we're going to create a parameter, hence the name. And most of the time, we're going to think about the parameter's time. So in other words, as we start our stopwatch and time progresses, creating a graph, either creating it going one way or going the other way. And that direction is going to be our orientation. So Desmos understands a lot of the time what we're trying to do, but in this particular case with the animations, we have to do a couple steps that might not seem terribly intuitive. Now, let's start off just plotting a point so I can kind of help you through what Desmos is thinking with some of this. If I just say, hey Desmos, plot 2, 2, no problem, right? It plots it for us. Now, if I say, I want you to plot t, and then let's say t squared. This may not be what we were expecting. Right? What we're going to take a look at is telling Desmos where to go for an x and a y depending on time. This is going to make a little bit more sense to us as we progress through. But if I try to tell Desmos your x is defined as time, so whatever your time is, your x value matches that. If the time says 1 second, your x is 1 second. If your time is 2 seconds, your x is 2 seconds. And then to get your y coordinate, you're squaring that. If we just take a look at this, Desmos automatically knows, hey, I'm going to have to make that t a parameter, a value that changes. And if we take a look at the default, a lot of times Desmos will just define, well, can't talk today, guys. A lot of times Desmos will decide what it wants to do with those t values. In this case, its default is to make t between 0 and 1. But let's say I make t go between 0 and 2. Notice that our graph increased. And then if I go to maybe 2.5, up even a little further. Now, let's say we're looking at -2. I'm going to cut it off at 2. We can kind of tell when we're doing 0, 1, 2, the orientation of our curve. In other words, what part is getting created as time moves forward. But if I were to do something like, just for example, -10 to 10, notice that this just looks like y equals x squared, just our parabola. Sometimes the way Desmos is thinking about these graphs, it's giving us the finished product instead of helping us animate it. So what we're going to look at is how to visualize these parametric graphs a little bit better and what's going on behind the scenes in terms of doing things by hand. So what I'm going to do is switch us over and then we'll come back to Desmos. I'm going to stop the screen share. And share my iPad screen. So in this particular case, we're going to take a look at the parameterization, it's kind of a mouthful, of t and t squared. Another way to write this is that x of t is defined by t and y of t is defined by t squared. You guys may see my little one who's right beside me. There we go, there we go. Okay, now you keep reading. I've got some company these days, Mommy. Especially when I'm not doing it during our class time. I'm sure you guys understand. But let's keep going. So if we're taking a look at this and we want to describe the motion, what we can do is create a table where we have t's, x's, and y's. So what I want you to do essentially is think about this t as an extra piece of information that's helping us create the parameterization or the parametric graph. So we're going to think about time as, in this case, it doesn't necessarily have to start at 0. A lot of times, depending on our scenario, it might make sense one way or the other to have negative time or not. But then think about what we're going to do with our x's. Our x takes whatever the value of t is and just mimics that back. So our x values are going to be 0, 1, 2, 3, and 4. And our y value is going to take and square that t value. So our y values are going to be 0, 1, 4, 9, and 16. So then when we take a look at this portion of our graph, or excuse me, this portion of our table, this is actually giving me 4 ordered pairs. Well, I can't count, 5 ordered pairs. And as we graph these and we move through time, it creates our orientation for us. So let's just create a quick axis here. So we'll start by plotting 0, 0, point number 1. Then if I plot 1, 1, and then 2, 4, and then, ooh, why don't we skip doing more than that? We'll just kind of do those first 3. Space here. But what you can see is that these 3 points are discrete dots, discrete points on our grid. But as I think about tracing out the path that it's building, we can imagine what's happening as I fill in. I'm really doing this. And in fact, if I were to only look at t values 0 through 2, it would cut off at that point. But these arrows here, typically when we do this by hand, will indicate the orientation by doing this. So let's take a look at how Desmos is processing this. I'm going to show you a couple of tips. So I'm going to stop this share and take us back. So part of the problem with what Desmos is doing, with what I was showing you before, is it's creating essentially the finished product when I just plot this part. And what we want to do is kind of tell Desmos to create the animation. So I'm going to turn this picture off because in general, when you're trying to visualize the actual motion, it's not where you want to start. If you just want to know what's the finished pathway and ignore the orientation, then just putting a set of parentheses, your X and your Y, is a good way to go. Now, again, we haven't really investigated why this is saving us time. At the moment, it seems like a little bit more work, but we're going to see this idea of parameterizing allows us to do a whole lot of things. So let's go ahead, and what we're going to do is create a slider. So I want to create a slider that actually gives me a time control. you guys may see that Desmos is saying, do I want to create a slider? And well, yes, I do. And you guys may hear their little one in the background making some noise too. But this actually allows us to plot points and not the finished product. So I will link this code up for you guys. I'll save this and upload it so you can kind of see how I'm doing this and use it as a template for other features or other graphs. So if I look at this particular one, notice Desmos default decides what my slider should be. Let's say that I want my slider to go between 0 and, let's see, I did 4 on there. That's good. And I want to go in steps of 1. So what this is actually doing is allowing me to start at 0, x equals 1, or excuse me, t equals 1, which is also x equals 1 in this particular case. It's not always. T equals 2, and then 3 is up above where we can't see, and then 4. So in this case, we're seeing the individual points as if we were doing it by hand, but Desmos is not actually plotting or tracing that path. If we want to trace the path, we actually have to do one more thing. So what we're going to do is kind of modify this first coding. And guys, I'm not, you guys know I'm Desmos medium, right? So sometimes I even have to stop and troubleshoot a little bit to make sure that I'm getting this right. But I'm going to do t squared, but I'm going to restrict my values for my t to be less than or equal to the value that I just did. So this looks a little strange, but what Desmos is doing is saying, I'm going to plot the t squared, and I'm going to trace out and restrict it to wherever my slider is. So in this particular case, I could even, like this very first one up here that's blue, ignore that completely. A lot of times we don't even start with that part. We know that that's what the whole picture would be. But if I start back at 0, and then I go to t equals 1, t equals 2, t equals 3, and then so on, notice it's tracing out the tip of the motion, and then it's highlighting and tracing over the curve that's being created. Now, let's go ahead and say I want to modify this slider. So you can just kind of click on it, and let's say I want to go between -2 and 2, but I want to go in steps of 0.1. Even go smaller steps. Kind of helps you have a little more control over this. So notice what's happening here. Desmos, sometimes you have to kind of do a little bit of playing around with this, because notice right now you don't see anything, but then all of a sudden over here you start seeing stuff. Notice when we set this up, our t value is less than our slider, but between 0 and 1. What we actually want to do is just kind of whatever we're using for our slider values, just go ahead and repeat it here. In other words, it allows you to trace out wherever you're making your slider. So again, a little bit technical here, but now if I pull my slider all the way back and start, that change in the coding allows us to start tracing immediately rather than just tracing when t is 0. Okay, so this portion of the graph, my smiley is, my bottom of my smiley face, is created by doing t squared for values of t between -2 and 2 inclusive. So what else do we know that has worked this way? Well, one thing that we've studied quite a bit so far is actually Ferris wheels. So if we think about the very beginning of class, we had a rider, and that rider is rotating on the Ferris wheel, and we're thinking about tracing the rider's position. But as we're tracing the rider's position, we're actually tracing out a circle. And if we think about the unit circle, right, not all Ferris wheels are unit circles, but we can start with the unit circle and build from there. So we've actually been doing this idea of x coordinate, y coordinate, and an angle. It's the same idea as a parameterized curve. In this case, we're doing a time, this parabola, a time in x and a y. But when we move to the unit circle, we're thinking about an angle and then an X and a Y. It's very similar thinking to that Ferris wheel movement. So what I'm going to do is take us into actually, instead of doing that, let me leave us here. Here's, I'm going to have you scoot a little. And I'm going to modify this coding, just so you can kind of see what I'm going to do with it to do a different example. So I'm actually going to this time look at cosine t, sine t. Now, right now, everything's turned off. So notice my graph is not filled in. If I think about my x values are cosine t and my y values are sine of t, then I'm going to create a circle if I trace out angles between 0 and 2 pi. So this idea of angles is like our time. Instead of doing 2 pi, let's just play around with this a little bit to do 5. Okay, and I'm going to turn it on. Notice I traced out part of a circle, but I haven't gone all the way to 2 pi. If I change this to 2 pi, I've got my complete circle. If I did something like pi, I've got half a circle. So in this particular case, I'm going to have to modify the rest of the code if I wanted to do that tracing. Let's actually think about that whole circle. So if I let my time run between 0 and 2 pi, or my angle between 0 and 2 pi, my complete picture. But if I want to trace out where my writer is at any time and their path at any time, I can go ahead and do cosine instead of t time. Okay. And then instead of, I don't want this squared, what I really want is sine. So cosine t and sine t. And then right now we don't have anything turned on. So let's turn this piece on. And as I move my slider, notice what's happening right now. -2 to 2. That's not our typical window. Let's go for the slider value 0 to 2 pi. So kind of matching it up in terms of trig thinking. So if I go ahead and modify my slider, there's 0. And notice this piece tracks my person's movement, my rider around the Ferris wheel. And then if I modify the tracing aspect, this last part, cosine t, sine t, I should almost be good to go. What I need to do is just modify the range of my t here to match up with what I want my slider to be. This is kind of a little bit more programming feeling, but again, you guys are going to have this built in, so you're not going to have to recreate this on your own. Certainly, you're going to see it in the Desmos activity and go from there. All right, so turn that on. I'm going to push my slider back, and notice now it's tracing my point, and it's tracing out my circle. All right, so that looks pretty good. So what we want to do now is understand a couple of different things. I want to walk you through part of what your Desmos activity is going to ask from you, because the first couple slides, what they're wanting you to do may not be clear. It kind of just helps to have that direction. And then I'm going to take you over to your WebAssign and show you a couple of different things that you're going to have to do there, as well as a couple other examples. So let's take a look at this one. In this particular one, we kind of worked through that, and I'm going to fast forward through a couple of these slides till we get to this one. This is actually, I think, slide 4. But for this one, it says match the point. The path of the point is shown as you change time. So this is kind of like the behind the scenes programming for what we just did. As I move this slider, notice its values between 0 and 3. Notice it's tracing out, it looks like the top half of a semicircle. Oh, it doesn't quite go to pi for my slider, so I don't quite hit my x-axis. And in addition to pulling the slider over here, you can also pull this slider on the right. So what we are actually trying to do, if we notice the point, the open circle at the end, we're trying to match that point. Now, for example, when we start, that point is 1, 0. But that's not what this is looking for. Oh, sorry, not 1, 0, 2, 0. No, sorry guys, I'm looking at my slider here and I was looking at the 2 there. Sorry, the orange one is at 1, 0. So notice it fills in our red dot. But now if you drag your slider, notice that red dot does not move at the front like we want it to. In other words, it's not the leader tracing things out. This 1, 0 is static. What we really want to do is think about the path that's being created. It looks like we're tracing out the top half of the circle, a semicircle. So what you're going to have to do is use that time, kind of with the subscripting. Sorry guys, a little distracted by dancing kid over here. Where I like to live stream during class time. But anyway, hopefully it'll provide some entertainment for you guys watching this. There's cosine t, sine t. And notice if we are rotating with the unit circle and there's nothing going on with my rotational speed, this is going to match up pretty well. So when I look at this, notice now how our red dot moves with what we're doing. Okay, so that's kind of the idea on this one. What we're going to take a look at now is reversing our paths and changing our speed. So think about the different things that we could have done on the Ferris wheel. All of it is going to translate. For example, if we're moving the opposite direction, reversing our rotation had to do with putting our negative in front of our t. If we're making our Ferris wheel bigger, we're changing the radius. If we're spinning faster, we're changing our rotational speed. All of those things you're going to get to experience in these slides. So, for example, let's take a look at this one. If I drag this one, ooh, I'm rotating the other direction. And notice it's going all the way through almost a complete rotation in this case. So in this particular one, think about if you were to rotate, normally you rotate through angles of 0 to 2 pi, but our time is getting us there in pi. And then also, if we think about what's different from this one, backwards from the previous one, notice this one, the first one, we were rotating counterclockwise. Now we're rotating clockwise. So we have two things to kind of adjust for. The first one, the easier one to adjust for, is to think about rotation. So I'm just going to put on the exact same thing we did to start last time. Cosine time, parentheses, and then sine of time. So in this particular case, notice if I pull my slider, things are not looking good, right? So part of it is if I want to reverse the direction, change that direction. So now I'm rotating, but do you see how my red dot is lagging? It's only kind of going through half of the path. Notice if my path is pi over 2, my red dot is close to pi over 4. What this is saying is we really should be going faster. So try it faster. You could go twice as fast, speeding up that rotational speed, that angular velocity by a factor of 2. And notice that works. So these ones are not designed to be necessarily super tricky, but you're going to be able to manipulate the radius, manipulate your rotational speed, and make sure you have a grip on what's going on here. Now, I'm going to take just a minute and walk you through what would happen. Oh, actually, let me share that again. Walk you through what would happen if we were looking at our t and t squared example. In our t and t squared example, if we wanted to reverse what's happening. I'm gonna get rid of my sine and cosine here, just to kind of illustrate how to do this part. And we were doing -2 to 2, the parameters we were looking at here. Oops, forgot to square that time. Would have helped if I'd just saved that page, I think. So notice I'm getting rid of all my sine and the rest of this. And so if I look at this one, last thing I need to do is just change that. So again, you'll have this coding. I'll send it to you. I'll leave the T and T squared in. And my parameters here, I want to change. So at this point, this is what we just created. Again, try to save some of your pages as you're doing this. That'll make life a little easier. And then what I want to do is go ahead and show you what happens if I reverse. So if I put a negative in front of the time, now I'm putting it inside my parentheses here. That's on purpose because kind of like with the cosine and the sine, you're putting it in with a T before you square it, kind of like you did the sine and cosine there. Okay, so notice this time, if I pull my slider back, we're not doing clockwise and counterclockwise, but we can think about right to left and left to right. We're reversing the direction of what we had before. All right, guys, so I'm going to stop our share for right now. I'm actually going to do a part 2 where I open up your WebAssign and look at it, but that will come. I'll just start a new video on that one.